on? Yeah, great. So that was an excellent introduction, I think, to Reactive by Martin. I learned a lot. It's always fun to hear. I mean, war stories and everything built from experience and stuff. This talk is about the second trait, the scalable trait. And I think scalability is really something I'm passionate about and been passionate about for a long time. I remember taking the first distributed computing course in school, and I got thrown into this very alien, very amazing world about distributed computing. And I'm also guilty of doing things. Being part of the early Corba community, and been even promoting Corba and EJBs and RMI and all that stuff. And I learned a lot, I'd say, over the years. So it's been a lot of agony and a lot of pain. I've bled a lot, and so in this talk is still sort of a mixed bag of things that things that work and things that I believe do not work, and some of the stuff is sort of pretty hard. Especially the distributed computing part, the scaling out part is usually pretty hard. But I think you can actually distill it to a few sort of fundamental practices, and that will get you very, very far. And I hope that will be sort of the takeaway from this talk. So the agenda is that we have a little short introduction talking about what is scalability, what is scale on demand, why do we need it, etc. And then I'm going to talk about scaling up, and then scaling out, and then sort of bring it together. So let's get started. You've seen this. These are the four traits. Martin covered responsive, up on the top. And in this talk, then, I'm going to focus on the scalable side of things. And the scalability really builds on top of what Todd is going to talk about by the end of the day, event-driven. So event-driven is all about the async, loose coupling, non-blocking, etc. And I think that's really the true enabler for scalability. I think it's impossible to actually build a fully scalable system without that. And I hope that will sort of also be very clear during this talk. So what is scalability? Yeah, Martin Thompson defined it like this, sort of a bit humorous. The house in which Armdolls wakes up very early each day when the rules with an iron fist, right? I don't know if it's this guy, but he looks pretty angry to me. Even say, "Die by my hand." And Armdolls is really a guy that you should watch out for. He will come back and slap you in the head. If you go to Merriam-Webster and ask for what the definition of scalability, it says that it's capable of being easily expanded and upgraded on demand. And I think that's what captures actually the essence of what I think scalability is all about. If you ask Werner Vogels, he said that about scalability, a service is said to be scalable when we increase the resources in a system. It results in an increased performance in a manner proportional to the resources added. And it sort of makes sense, but when I asked Victor Klang, the chief architect who actually made it here, even though he's expecting twins very soon, asked him about sort of looking over my slides, he said, "Yeah, Werner, he seems to confuse performance and scalability." And that sort of brings me to what is really performance and what is scalability and how do they sort of interact. And it's actually pretty fuzzy. A lot of people have different definitions on what it really means. So my definition, the one that I usually use, and might be wrong, but is that performance is the capability of a system to provide a certain response time, while scalability is the capability of a system to maintain that response time as we add resources to deal with increasing load. And when I showed Martin Thompson that, he said, "Yeah, that's overgeneralized." Right? So so when you look at it, when you ask different persons, you really get different sort of views on this. And I think it's because it's a complicated subject. Performance is really three things. It's like dealing with latency, low latency, high throughput, and scalability. And they're sort of tangled and interact with each other. So, I mean, I'm going to throw the question out here today then. What do you think is performance? What do you think is, and how does it relate to scalability? I mean, it sounds like a good thing to discuss over beer perhaps tonight. So what does it mean to scale on demand? Yeah, scale on demand is extremely important. It means that we need our applications to be expanded according to its usage. We need to be able to sort of react to increasing load over time. I mean, it can be both sort of unpredictable spikes that we haven't planned for. It can also be predictable things like we know that over Easter or Christmas season or whatever, depends on our domain, we know that the usage of our application will grow. And we want to both scale up and down and in and out and in as well. We really want to sort of deal with things like rapid growth and things like that from a sort of technical perspective. But it's also nice from a business perspective. And changing business requirements and sort of live up to this promise of cloud computing that utility computing, that you only pay for what you use. And you don't have to worry about having too much sort of hardware idling there because you know that you might get spikes eventually. Or the other way around, you don't need to worry about having too little hardware and lose sleep of that. You can actually pay as you go. For me, that is really what sort of scale on demand is and why I think it's important. So if we now sort of go back in history a little bit and look at how the rules of the game have changed, because they have really changed fundamentally the last 10, 15 years. And not everyone might actually be aware of it, even though we live in this all day. No. So if on the left-hand side here we have sort of requirements for the world that apps in the 60s, 80s, 90s, or probably early 2000 were written for. And on the right-hand side we have apps the world that apps are written for today. So apps used to be written for single machines. Today, we usually deploy our applications on clusters of machines. That means that we have a distributed computing system from day one. And that has big effects on how we need to design our software and think about software. So on all these machines, we used to have single core processors. I mean, the von Neumann architecture worked really well with mutable state and things because it really worked on. It only ran everything ran sequentially. But today, it's really hard to find a single core processor. Even my phone is a quad core processor today. And since it's a vastly new world here, we need different tools to solve that will help us. We need to raise the abstraction level. We can't munge around, I think, with threads and locks any longer because we will lose our sanity. I mean, things are too hard. Apps used to be written for at a time when RAM was really expensive, and today RAM is really cheap. And I think that also opens up for things like in-memory database, in-memory caching. I mean, do very efficient and fast replication across machines and so on. Disks used to be expensive. Today, disks are really, really cheap. And this means that there's really no reason to delete data any longer. These in-place updates has to die. Also the traditional ways that SQL databases are doing it. I think there's really no reason to not keep history around because disks is so cheap. Networks used to be really, really slow. Today they are immensely faster. It's often faster to write to the network than to writing to disk, and that also opens up for a lot of sort of possibilities when it comes to really efficient replication and so on. And apps used to be written for very few concurrent users. I mean, hundreds. I mean, thousands was sort of a big app. But today, since most applications are exposed on the internet, we open up for potentially hundreds of thousands, millions of users. And all these users, I mean, they used to create really small data sets, but since there are so many of them, the data sets are massive now. And these data sets are both like produced by the user, but also from the server up to the user. And we need completely different ways of like moving around all this data, and streaming the data up and out, and analyzing it and so on. And applications used to be okay if they had like seconds of response time in latency. I remember, even when you had to actually go and manually refresh the browser page. Today, users are extremely impatient. If there's the slightest delay and happens more than once, they will go somewhere else, and you will lose users, or you will lose money unless you live up to these SLAs at all times, not just in blue sky scenarios, but also when things are failing and things start to go wrong. So it's a vastly different world. And around the corner, we can expect there's billions of devices, this Internet of Things. I mean, we have smart cars, health monitors, and we like thermostats, the refrigerators, all that stuff will be connected. And the GSM Association expects that in about 2020, you will have like 24 billion devices all connected. And many of these devices will run way more than 4 cores. I mean, in a sort of not so distant future, I think it will be hundreds of cores, but thousands of cores. And heterogeneous multi-core is really here to stay. I mean, today we have like CPUs, GPUs, FPGAs, and so on. And so I think all of this means that we need a very different way of building systems. I mean, what kind of servers will actually be able to hold up for billions of devices, right? I think that reactive might not be the final answer, because there's no such thing, but I think it's part of the answer. And that's why I'm really excited about that. So just some examples of stuff that I'm really excited about. For example, this is an example of 42 parallel boards. That means 756 CPUs, all consuming less than 500 watts, at a price of, I think one is like $99. It's like 4,000 euros or dollars. So it's extremely cheap. You can really run this in your homes nowadays, right? And here we have this Wunderbar. I just love the design of this. It's sort of it's a chocolate bar. It's like Internet of Things starter kit for like a little bit more than 100 euros. But it contains like sensors that you can put on basically anything, like for like light and accelerometer, gyroscope, and it has all built-in Wi-Fi. It's pretty cool stuff. And this is one of my favorites. I'm actually having it on me constantly. Is this Basis health tracker? That has make sure that I do my daily exercises and track sleep and stuff like that. And all of these things, they are getting extremely cheap, and they're getting more and more advanced, producing more and more data. So one example of how fast things are changing is that in the 1980s, I mean, a Cray 2 a Cray 2 was considered a supercomputer. But today, the iPhone actually has more processing power. And the Cray 2 was immensely expensive, but an iPhone basically costs nothing compared to it. And this is an example of what Peter Hitchens called cost gravity. And it's really a sort of a generalization of Moore's law, that technology is getting exponentially more advanced at a cheaper and cheaper price. And this is like truly fundamentally changing the way we approach technology today. I think it's extremely exciting, but also terrifying in a way for us as developers. How will we be able to keep up with all of this? So, starting with scale up. Scale up means that we need to, in an efficient way, utilize multi-core architectures. So scale vertically. Okay. So if you look at modern sort of CPU architecture. Martin already talked a lot about that, so I don't need to go into too much detail about it. But for example, the memory management, it does some pretty advanced stuff with this sort of prefetching algorithms, the cache coherency protocols, and invalidation and stuff like that. And if you look at how CPUs are designed, they have this hierarchical cache. So you have like an L2 and an L1 and L2 and an L3 cache. And this image is a picture of the Haswell processor. The Haswell processor has like 2, 4, and 8 cores, and it has one L1 cache on about 64K, and an L2 cache about 256, and an L3 cache between 2 and 8 megs. And accessing that, I mean, accessing the 2 local caches, L1 and L2, is really, really fast. But it gets more and more, it gets higher latency. I mean, the further you get away from the processor. And the same thing if you look at NUMA, right, that Martin already talked about. Memory sort of sitting on the same socket is really, really fast. But memory, going across to fetch data elsewhere is pretty expensive, around 40 nanoseconds, as we could see in Martin's slide on the same thing. And also today's CPUs, they are really extremely efficient, so efficient that they normally have to stall, waiting for data to be fed to it. So the bottleneck is usually how the memory is managed. And it's always the case that local data is really, really fast. And that I think that has really big implications for how we design software. The CPU is really gambling. Martin brought this up as well, and I think that sort of gambling is sort of an okay metaphor, but it's not really accurate, because the CPU doesn't just rely on plain luck. It's actually trying to beat the system. Very, very similar to Rayman. I don't know if you've seen Rain Man. I think most people have seen that. So if you would ask the CPU, you would probably get a very similar response as what Raymond said, like, we're counting cards. Because it really tries to beat the system by being sort of outsmarted, or actually stay ahead of it, more to say. And the CPU sort of takes 3 different bets. First you have like regular caching, the spatial bet, usually LRU caching. No, the temporal bet. Then you have the spatial bet. That means that it tries to, I mean, it's data close to each other in code, I mean, are sort of assumed to be used frequently together. And it also does a lot of advanced things when it comes to how the application is being used, right? In the terms of patterns, trying to detect, like, it does branch speculation, try to detect patterns in the code. For example, if you're iterating over an array, try to like do prefetching and to read in, it's almost like stay ahead to make sure that you can feed the processors really, really fast, continuously. And the good thing is that even though this might sound pretty challenging, pretty tough, it's not that hard actually, because good practices and clean code really matters. I mean, things like using like really small methods that does one thing and one thing only, and that composes well, like functions in functional programming are supposed to be, at least, and use very simple logic, right? As little branching as possible, and in general, don't try to do clever stuff. I mean, clever stuff usually will just be, I mean, come back and bite you, right? Because the CPU assumes simple, clean code, and that's what it is really good at optimizing. But in general, you can say that if you make sure that your memory is local, then you get up for a very smooth journey. So it's like sharing nothing and keeping state local is really matters. And that also will help you minimizing contention. That is really one of the main killers. So I think 2 things really matters. I'm going to look at each one of them. Locality of reference, we want to maximize that. And we also want to minimize contention. So making sure that data stays local to its processing context, where it's actually being used, is extremely important, because you don't want to like send data around that's something that really will slow down things. So co-locating data, make sure that they stay on the same cache line. Ideally, as Martin said, like pin threads to cores. I mean, I usually live and breathe in Java, and then that's really not an option. So we have to resort to other strategies, and some other strategies can work fairly well, regardless. Like things like using the single writer principle, for example, using append-only logging, having a single writer just writing sequentially to disk, and things like this, using batching and so on. But in general, in general, contention is the second sort of biggest scalability killer, I think. And so some common points of contention is, I mean, where will this guy show up? We have both sort of the physical layer and the application layer. So if we start with the physical contention points, I mean, we already talked about CPU and the memory. We also have things like I/O, like network I/O, file I/O, I mean, regular database access. These things can really be where you get a lot of contention and the application sort of stalls. Application contention points, I mean, are like, if you look at the primitives, you have like synchronized blocks, for example, or like regular high-level locks, like you have concurrent locks or like barrier latches, these type of things. Even optimistic concurrency, which I think is a great tool in the toolbox, can also be contention points. I mean, if you have really high contention, then it can be hard to make progress. And that's also something to watch out for. I mean, overuse of volatile variables can sort of exhaust the memory bus as well. So everything can be misused, right? And sort of, Java concurrent has a lot of really nice data structures for concurrent access, but overuse of those and sharing too much, even though they are reasonably efficient, can also really introduce contention points. Same thing like with immutable persistent data structures. And in algorithms as well. I mean, normally algorithms where you have some sort of join point, right? So you have fan out and then sort of fan in, like aggregation phase, can also be real, I mean, really things to watch out for, like scatter gather and map reduce type of work and fork join and things like that. So in general, you can say that you should never ever block, because I mean, as Martin said as well, I mean, I'm recapping, he stole some of the main points in my talk, which I think is good because they are really worth iterating over and emphasizing, is that thread wake-ups are extremly important. If you block and the context is transferred and you need to like signal a thread to wake up, it can be up to like 700 nanoseconds, which is extreme, which it doesn't sound like much, but it's like an eternity in this when you think about the context. So I think if you really need to block, which you can do sometimes, then you should really first don't use a single thread at runtime first, right? Enough said. But you should rely on things like managed blocking, like you have, like in Akka, for example, or the fork join pool, to give a hint to the process to the scheduler that I am going to block, so he can allocate more threads. Another very important thing is to sandbox things, to make sure that one component that does blocking doesn't like steal all your threads and impedes progress on the rest of the system. You can actually make sure that you give that component an n number of threads. And if you want to exhaust his own thread pool, that's fine, but you can still make progress in the rest of the system. Another important thing is really to fully embrace asynchronous message passing. And I'm sure that's something more that Todd will talk more about in event-driven. But what it really gives you is a system that is sort of concurrent by design. Instead of sort of tinkering around with low-level sort of plumbing, like threads and locks, etc. So then you raise the abstraction level to work with how events flow in the system. And the nice thing with that is business semantics. That's actually value for application, and that is something that we as humans are very we're very used to, it feels very natural to think about things that way. I mean, everything that we do today is fully concurrent, and it is message-based. I mean, it's event-driven, really. That's how we all communicate, and we don't even think about it. So like trying to shoehorn everything into a really like sequential world is actually unnatural to us, even though we've sort of been sort of being told and been thinking about this way of programming for too long. So it's I think that it also gives you a way to write more like loosely coupled systems. That makes it easy to both write the system and maintain it and understand it and evolve it over time as well. And I usually tend to see that for people starting with asynchronous programming, it might feel a bit alien initially, and you have a pretty high sort of, I would say, but a higher initial hit of essential complexity. I mean, the complexity that's actually needed for the domain, but also needed to get all the nice things that the reactive has, the scaling out and the fault tolerance and all these things. But then it sort of usually stays fairly constant. You have very low sort of accidental complexity. While if you write this like a synchronous system, then it really usually feels very familiar to begin with. So you have a sort of fairly low in sort of initial essential complexity. But as the system grows, it easily gets out of hand. You get drowned in all the accidental complexity of using like shared mutable state and really coupled systems. And there are a lot of great tools for this. I mean, Eric talked about one of them for us in the keynote. I mean, RX, I mean, you can use actors or Erlang, Akka, I mean, future composition, pipelining, explicit queues like message-oriented middleware type of things, MPI, if you're in C and stuff like that. There are many ways you can do it. So the important thing is to change your way of thinking, really. So how should we design algorithms then? I mean, I think we should learn from Caesar. Right? Go back to and see how like this old-time winners actually solve the problem. Divide and conquer is really a great way, and this means like splitting up our work into like small, isolated, discrete, fully independent, if possible, tasks. And ideally, we want to have algorithms that gives us embarrassingly parallel sort of tasks that doesn't have any coupling at all. But sometimes that's not always possible, and often you have sort of join phase and so on. So if you do that, if you split up your work like that, then you can use pipelining, which means that you have like well-defined stages that your events like flow through. And these pipelines, they can be synchronous. Sometimes synchronous is actually the best way to really scale, to minimize. I mean, to maximize locality reference and really minimize the contention. Then you just run on a single thread, or they can be asynchronous, running on a thread pool, and often there are sort of combinations of that. I mean, starting with we're trying to get like fully synchronous pipelines. And if you can sort of max out on the CPU like that, then I think it's all good. But then you need to make sure that you never ever block, because if you block, the pipeline stalls and things get hard. And then it's an opportunity to sort of add asynchronous stages. So it's usually a mix between both. You probably heard about stage event-driven architecture, SADA. So they used to be very popular about 10, 15 years ago. And I still think it's a great example of something like this. You can build your own very easily using actors, or using something like LMAX disruptor, for example, or reactive extensions and things like this, like streaming data. Another great pattern that I think we all should know is it's a single writer principle. Writing things sequentially to I/O is really, really fast. Then you have sort of really no contention. It's very common to see when you have multiple producers writing to a single I/O device. And the problem there is that's a contention point that can really make your application really, really slow. This is when Armdolls really comes back to bite you. Instead, I mean, adding something like an actor or a queue or disruptor or something in the middle that just grabs all your requests and then writes it down completely, fully uncontended down into the database, or down out on the network or whatever, can really massively improve. You've probably heard about append-only logging and so on. That's something that comes up a lot when talk about event sourcing and so on. And it's really a nice way of dealing with it. So to quote my dear friend Victor Klang, he tweeted this a couple of weeks ago. I think it was a good sort of intro to immutable state. But as we all know, immutable state, it has a lot of nice values, right? Or nice properties. It's like gives you a code that doesn't lie, code that you can trust, stable values you can actually share between threads without losing sleep at night, and so on. And there's been a lot of talk about immutable state and how it relates to concurrent scalable systems. So I just want to have some comment on that. I think immutable state is great to represent facts, things that have already happened. Like see them as values. For example, using like database snapshots or messages between concurrent components and so on. But I think they are less ideal as to use as a working data set. Even though you can share them, I think that the best way, the way I like to approach the problem is instead to use a share-nothing architecture in which I then can use mutable state within. And that's usually a lot easier to understand and sort of reason about as well. And then use immutable state as my values that I send around, that I publish for reading and so on, when I talk about facts. So Martin has already talked about Armdolls Law, but I think it's really important to stress that it needs to be async and non-blocking all the way down. Armdall will come back and bite you. I mean, you remember this guy? He still looks pretty pissed off, so I think we should really try to stay away from him. And I think the best way to do that is to fully embrace a share-nothing architecture. And if you have a share-nothing architecture together with async message passing, a fully event-driven core, that gives you automatically great locality of reference, because the data that you mutate is isolated in a safe world, right? The messages might fly around asynchronous in a totally sort of non-deterministic world, but if inside my little safe box, I know that I'm fine. And that has a lot of good implications, both on scalability, but also in the way we can reason about code, I think. So in general, I think share nothing together with async message passing is the way to go. Talking about scale on demand, I mean, when it comes to scaling up, we can do some things. Like we can have like adaptive thread pools. Fork join is a really great example of that. I mean, we need to have models to deal with back pressure. I mean, so we can like do graceful degradation to not like fully overwhelm our system, like some of the things like Eric talked about. And I mean, you can circuit breaker, manage blocking is also one way of doing that. But I think that to really scale on demand, really truly do that, we need to have a way of adding resources to our system. And we can't do that when we scale up on multi-core. The topology, if you may say, or the set of resources that we have that we can use is fixed. So I think we need elasticity, being able to like add and remove nodes, or I'd say resources on the fly. And this brings us to scale out. Scale out is really about having a way of managing elasticity and have very efficient utilization of sort of cluster cloud computing architectures. And I think it's nobody can have missed that distributed computing is really the new normal. You can't really escape it, even if you want to. So we need a way to manage that and deal with it right? And most applications today have some sort of mobile connection or talking to some sort of cloud service, REST-based or whatever. We most use some sort of NoSQL databases or big data, whatever. Guess what? All of that is distributed and has a lot of the same problems that we have that we're trying to solve the last like 30 years in the distributed computer sort of field of computer science. So there's a lot to learn from experience and from history, I think, how we should approach this sort of new world, you may say, when things aren't that easy any longer. So what is the essence of distributed computing? Well, it's two things. It's to try to overcome that information travels at the speed of light. Sorry? You can't break the laws of physics. This means that it is increased latency in our application. And that has a lot of implications. And the second thing is that independent things fail independently. If you run things on a distributed system, then you have the network, and the network is really inherently unreliable. It is impossible to know if the increased latency when I ask another node is because he's down, he's actually dead, or if it's just slow, or if it's doing GC. It's actually not possible to know. And this has a lot of implications. Things also fail at a much higher rate in a distributed system. So we need a way to manage that and sort of embrace that way of thinking, I'd say. Martin already said that we need to think distributed all the way because, I mean, even our quad-core system running NUMA or something is already a distributed system. Amen to that. That's the only way we can really make things work, I think. So in a distributed system, then you have your nodes. And each one of these nodes have sort of completely isolated memory, right? It's not possible to share memory between nodes. So you need some sort of middleware, some sort of transport layer. It can be underneath, doesn't matter, but some way for these nodes to communicate. And if you look at the meta level, sort of each one of these nodes might sit in the cluster, that might sit in the rack, that might sit in the data center. The same problem applies across all of these sort of levels. That you have that sort of isolated machines communicating with messages. And I think that we all know that, I mean, distributed computing is extremely hard. Right? We all been told that, and I think that's true. But I also think that solid principles can make it manageable. You probably heard about them in Peter Deutsch's 8 fallacies of distributed computing, and most of them are, it's good to have in the back of the mind that network is reliable. It's not. It's really extremely unreliable, and that will have big impact on how you design your code. Latency is a lot higher. Bandwidth, network is secure. Yeah, right. I mean, even if the NSA can even like put in plugs on the Google internal sort of connections. I mean that's really a fact that's not the case any longer. That topology does change, and it changes as you use the application, as business requirements change, and so on. There's one administrator. I mean, this really shows. I mean, you know that there is a high rate of human error. Someone will go in and screw things up, right? You can't just trust that you have full control over the system, at least if it's a big one. And the networks are not homogeneous any longer. They're heterogeneous, and that also has big impact on how we design software. So before we go on, let me also let's pay a visit to my own graveyard of distributed systems. Now, things that I'm sort of being affected personally, I think that really doesn't work. And the top one is the distributed shared mutable state. I mean, shared mutable state is bad as it is. Distributed shared mutable state is really an evil to the power of n, where n is the number of nodes. And things like serializable distributed transaction, like XA, it really doesn't work. Synchronous RPC, guaranteed delivery. No, it's just lies. There's no such thing as guaranteed delivery. And distributed objects, I mean, Corba and EJBs. Martin Fowler said it really well when he said that they suck like an inverted hurricane. I mean, we shouldn't even go there. I mean, these things have been tried and proved not to work. There are better ways. But what should we do instead then? I think we should, I said, locality of data matters. And it matters even more in a distributed system, because shipping data around in a distributed system is even more costly. Right, so first we can look at some sort of classic techniques. First, simple stuff, how we can help with this. Sticky load balancing, for example, making sure that you route every single user request to the same node, not having his user session to jump across nodes, like in a sort of random fashion. Another thing is sharding, like you split up your work into buckets and make sure that you have some sort of hash function. You send request to that node that's responsible for that. That's also like to maximize the locality of reference. You normally need something like replication. Body replication is another thing that sort of fits very well with that. Basically, the thing sort of solves the problem that you can't replicate everything everywhere. So you pick a number of buddies, and you set a replication factor. It's usually around like 3 or 5 or something like that. And then you replicate to them. And you know that their data resides on these nodes only and doesn't need to be everywhere. The important thing to make sure then is that all your buddies are not on the same node, right? Because if that node or machine, if that machine goes down, then you're host anyway. And ideally, they shouldn't even be on the same rack, right? You like maximize the chance of actually surviving failures. Consistent hashing is another really good tool. It was sort of popularized by the Chord project, I think. I mean, this is an old distributed hash table, but it was sort of really taken mainstream. I think it was with the Dynamo paper, and it's sort of a classic strategy that used across all of the sort of, let's see, most at least the NoSQL databases now, and it basically. It works that you lay out your nodes in a node ring and you split it up into buckets, and then you have a consistent hashing function that sort of makes sure that you hash each one of these buckets with a specific data set. And then the nice thing is that then you get an even distribution of your data across the whole node ring, and supports naturally things like elasticity and repartitioning, and all the things are a lot easier. It also makes you, easier to avoid hotspots like high contention on a specific node, because you distribute out all requests evenly in the cluster. So both helps with locality of reference as well as minimize contention. But I think minimized contention is really the most important thing in the cluster. And in the cluster, you usually talk about coordination, but that's sort of the same thing. Coordination in the cluster is the biggest scalability killer, I think. So, but if you want to start looking at some theory quickly, we have like 3 models for consistency. We have strong consistency, and we have eventual consistency. We also have weak consistency, but that's not really useful for practical purposes. Let's focus on the strong and the eventual. Strong is defined by something called linearizability, and even though we have sort of the real definition here from this Hurling Wing paper from '91, I'd say that less formally, it means that a read will return the last completed write, regardless where it's happened, on any replica. And if you think about that, that's a very sort of strong guarantee, extremely strong guarantee, and it's also extremely expensive. So some sort of strong consistency protocols. I don't know if you heard about Viewstamp Replication. It came out in '88. It was just 1 year before Leslie Lamport wrote his Paxos paper, and after in a couple of years wrote Paxos Made Simple, because it was insanely hard to understand, and that was also even more hard to understand. Viewstamp Replication, unfortunately, I think was something that was almost forgotten. It's a way simpler model than Paxos, because it separates, sort of the replication from the actual logging, and so on. So most people actually embraced Paxos, and it became sort of the standard for doing sort of consensus protocols and doing like strong replication between nodes. And I think that's really unfortunate. The Zookeeper guys came out with ZAB, the Zookeeper Atomic Broadcast Protocol, in, what was it? It was just a few years ago. But last year, this is John Oosterhout, and one of his students came out with Raft. The Raft is actually very similar to Viewstamp Replication, and it's a lot simpler model to embrace. And there are now implementations in almost any language you might think of. So if you need strong consistency, that's an algorithm, I think, or implementations that you should look at a lot more than trying to implement Paxos yourself. But as I said, strong consistency is extremely important. So if you use it, make sure that you only use it for the tiny data set that actually needs full consistency. And for the rest, use something else, right? Because I think different data sets has different guarantees, and you shouldn't like shoehorn everything into the same bucket, like people use when they have Oracle database. Like for simplicity, just let's shove everything down there. That's also a scalability killer. Think about data semantics, and use what's needed for that particular data set. Another sort of very important discovery was the CAP theorem. Most people probably heard about it. I don't need to go into detail, but it was something sort of conjecture that was coined by Eric Brewer. It was later proven, like 2002, I think, by Nancy Lynch. And it basically says that out of consistency, availability, and partition tolerance, you can only pick two at a given point in time. And the thing is that was hugely influential. It really sparked the whole NoSQL movement. It was sort of popularized by Dynamo, and then the whole NoSQL movement took off. But the thing is that now in retrospect, we can see that linearizability is something that it's really not needed in most cases, and the CAP paper sort of assumes that it's always needed. But systems aren't just black and white. And why sacrifice either consistency and availability if partitions are rare, which they're reasonably rare. At least, they don't happen all the time. So instead of just fully adopting CAP, I think we should look at it and learn from it, but have a more dynamic, more sort of healthy relationship to it, and loosen up the guarantees when needed. Eric Brewer even wrote a great paper on that perspective called CAP 12 Years Later that I really sort of encourage you to read. So this brings me to eventual consistency, because that's really what CAP is all about. And eventual consistency basically means minimized coordination. It gives us more headroom to work with things like scalability and failure. Having high available systems. And so the definition of eventual consistency can be that the storage system guarantees that if no updates are made to an object, eventually all accesses will return the last updated value. And the emphasis is on eventually. Eventually is not like well-defined. It depends. And this also gives you some headroom. What are your SLAs? You first need to define them, and then you know how much headroom you have for scaling out and to deal with high availability. But the thing is that most of these databases are key value stores. The Cassandra is sort of column store, but Dynamo and Voldemort and most of these are key value stores. That's what comes from the from the CAP theorem Dynamo angle. But there are some very interesting research done lately around providing eventually consistent, more richer data structures, and they are called CRDTs. And I have really high hopes for CRDTs because they are all about minimizing contention, minimizing coordination, so to speak, in a distributed system, but still provide you with rich data types. There are CRDTs, there are sets, maps, graphs even. And how they work is, I mean, so the important thing with all of these is that they have a sort of what is called a monotonic merge function. That's sort of they have, so everything sort of state change is monotonically increasing. There's no way back. And there are two types of CRDTs. We have CVRDTs. V stands for convergent. They are usually what's called state-based. And this means that they keep the history in the actual data type, which can be sort of expensive sometimes if it's a long history that you ship around. It also has this garbage collection problem. You can't have that grow forever. But for certain type of problems, I think they are really nice. And we also have CMRDTs, like commutative replicated data types, and they are what it calls operation based. So they have sort of higher requirements on your infrastructure because it requires sort of a reliable broadcast channel. Because what you do then is that you do not record every single state change, but you actually record the operation that led to the state change. Okay. But the question is now, if we can't have a fully eventually consistent system, but we need to provide transactional integrity somehow, what can we do? Go back in history. I mean, this is not that old, but it's a really highly influential paper. I think I think it was, everyone should read this. It's by Pat Hell, and then one quote from this paper is like, in general, application developers should simply not implement large scalable applications assuming distributed transactions. But if we can't use the distributed transactions, then what should we use? So let's step back and look at some sort of tools, how we can actually achieve this anyway. Domain events is one. Domain events represents facts. They are immutable, and they represent like something that have already happened. Like things like customer relocated or cargo shipped or invoice paid or something like that. Things that cannot possibly change. If we then use that together with an event log, an event log is basically a database for your domain events. Fully applying sort of the single writer principle, append only logging. And there's many ways you can sort of log. You can use like memory mapped files. You can rely on something like level DB, or you can like store it in a SQL database even, or like using one of these NoSQL replicated databases or whatever. It really doesn't matter. What matters is sort of the way you think about the problem and the way you split up and design your work. Okay, so the event log is that it's like a database of facts. It stores what's already happened. And the important thing is that knowledge just grows. Okay, you never ever delete anything. As I said, disk today is cheap. There's no reason to delete stuff. And if you look at it, you can look at it sort of from two different perspectives. Either you have one single event log. That's basically the datomics model. That means that you can have a fully consistent data. You can take a fully consistent snapshot, basically, of your current state at the other end. That gives you like full transactionality, but at the cost of perhaps limiting scalability. The other is actually to stripe, to shard that, to have multiple different sort of components, all with one single event log. And that is something that's that ties very much into what the DDD community is doing now with aggregate roots. Aggregate roots is basically the entity that represents a bunch of other entities, and that can be your transactional integrity, like boundaries. So you have each aggregate root, you have full consistency, but that means also that between these aggregate roots, you do not have full consistency. You have eventual consistency. So if you want to use joins and stuff across many of these, it is eventually consistent. And that's not all good, but it's a price we have to pay for like unlimited scalability, which I really think that we can get if we design our systems like this. But again, I think now I hope at least that it's clear now. Like again, share nothing architecture is really the way to go. We need to fully embrace that. To have good data locality, shipping data state around is really expensive, and also sharing state introduce contention and coordination bottlenecks. Okay. So if we want to scale on demand, I really think that there's one thing that should not be underestimated, and that is location transparency. Location transparency is not transparent distributed computing. I mean, you saw in my graveyard of distributed systems slide. That doesn't work. But location transparency actually is the other way around. It's being very explicit distributed computing, embracing the network, and embracing sort of fully the model of asynchronous message passing, because that's really how distributed components must interact. If things traverse across the network, it can't be strongly coupled. So this gives us one single model, like Martin also touched briefly, to scale both up and out. And I think that's the only way we can write systems. Since everything is distributed now, why should we have two models, one for scaling up and one for scaling out, instead of focusing on having one single way of doing things, and regardless if we scale up or not, regardless where components are running. I shouldn't have to care where the runtime actually puts a component right now. And this gives the runtime opportunity to actually optimize things by moving runtime components around, bringing it closer to the processing context to optimize locality of reference, for example, and communication and things like that. I think that's really the way to go. So if we bring things together, what I tried to highlight in this talk, right, is that you can think very much of scalability as these Escher's painting, the print gallery. I don't know if you've seen that, but it really, I mean that from large to small, I'd rather say, everything is the same. I mean, you can think about it as like, yeah, these machines, right, that all have isolated local memory, and the only way to communicate with something is like telling him to do something by sending a message. If we look at the problem like this, that means that the same design principles can be applied at any level in our application. So if we now look just like tie that back to our system, it means that this also applies to our whole stack from top to bottom. If the data center, or if on the cluster level, or on the node level, on the thread level, I mean down to the CPU, all the way down to the L1 and L2 caches, it's all will benefit from a share nothing architecture and through message passing. I think that's really the only way to scale. So that brings me to my final point, that scaling up and out are essentially the same thing. There's no difference. And there shouldn't be any difference in your programming sort of patterns in the way you design your system. If you do that, you're up for location transparency, and I mean, sky's the limit in how you can scale, really. However, it's really hard to design everything like that, but as much as we can, the better, I think. So, if you only remember one thing, remember to minimize contention and maximize locality of reference. I think that's the key message. And the way to do that, I think, is use share-nothing designs with local data. That will both minimize contention, because you can it's just you touching the data, and it will also maximize locality reference, but also minimize contention. And we can do that by building on a fully event-driven foundation, like we do in reactive applications. And Todd's going to talk more about that later. But I think the final point is also that we need to fully embrace locality of reference. And if we do that, I mean, scaling up and out is not that hard, actually. So by adhering to core good principles that have proven to work for ages, we can actually keep our sanity and write really scalable systems. So, yeah, 1 minute for questions. Or I don't know, I mean, instead of taking them now, I should perhaps encourage you to scribble them down, and let's take them at the clinics at 4 o'clock, where we can have a very engaging, lively discussion about these things. You might all disagree with me, and that's fine. I'm looking forward to that, actually. Let's see. And also, please remember to give feedback on all the talks. Go to this website and find the talk and tell us what was bad and what was good, and how things can be improved.
Big round of applause for Jonas, please, everybody.